Today we're diving into a breakthrough that could change how we store and transport methane, using graphene-coated nanoporous carbon. I'm Ben, this is Physics or Bust. Methane is a powerful fuel and a potent greenhouse gas. Safely storing it in high density has always been a challenge, but now scientists have developed a material that holds more methane per volume than traditional tanks, graphene-coated nanoporous carbon. We'll look more into the physics of this next, but first, if you like this video, you'd probably like this book. I've got a link in the description below. I do get a small commission, but it wouldn't cost you any extra. Let's break down what this means and the physics behind it. Methane, or CH4, is the main component of natural gas. Its energy density makes it ideal for heating, electricity, and even vehicle fuel. But conventional storage relies on either compression at high pressure, up to 250 atmospheres, or liquefaction at extremely low temperatures. Both methods are costly, energy intensive, and potentially dangerous. So what's the solution they came up with? Nanoporous carbon is a type of carbon that's riddled with tiny pores, nanometers apart. These pores create a vast internal surface area where gas molecules can adhere, a process called adsorption. 1 gram of nanoporous carbon can have an internal surface area exceeding 2,000 square meters. When you have tanks and storage containers coated with this graphene, you increase that tank or storage container's stability and its methane affinity. But how do you actually make the graphene coating? Let's dive deep into the physics of this process. The first part of the process is called chemical vapor deposition, or CVD. Methane gas flows over a heated metal surface, usually copper or nickel. At around 1,000 degrees Celsius, methane decomposes into carbon atoms and hydrogen gas. The carbon atoms diffuse across the metal's surface, self-assembling themselves into a single atom layer graphene lattice. By controlling pressure and gas composition, scientists tune the thickness and quality of the graphene. Once the graphene forms, it's transferred onto the nanoporous carbon matrix. This process uses a polymer scaffold to lift the graphene off the metal surface and then press it onto the porous carbon. The result is a robust, highly conductive coating. So how does all this help store methane? It's all about the van der Waals forces. These are weak temporary fluctuations in electron distribution within a molecule, creating temporary dipoles in the molecules that induce dipoles in nearby molecules, thus making an attraction between the two, and also creates an attraction between the methane molecules and the graphene surface. The nanopores confine the gas molecules, increasing local pressure. Graphene's smooth, highly ordered surface enhances adsorption energy. As a result, methane density in the pores can exceed that of liquid methane at ambient conditions. Think of it like packing clothing into a suitcase. If it's all just tossed in there, you don't fit as much as if it's highly ordered and positioned. So having the nanoporous carbon inside your container is like having a very organized suitcase, where it just fits more because it's nicely folded and pressed down. And that's what's happening with the methane atoms. They're being nicely ordered and pressed into all those little holes of the nanoporous carbon. It is worth clarifying, this material does not convert carbon into methane. Instead, what it's doing is storing methane harvested or produced elsewhere. However, in industrial processes, methanation can produce methane from carbon sources. Quick physics note, methanation involves using carbon monoxide or dioxide and reacting it with hydrogen over a metal catalyst, usually nickel. And this process also happens over high temperatures. And the process itself is actually exothermic, meaning it releases more heat. Alright, coming back off that rabbit trail. Graphene-coated nanoporous carbon is an example of material science solving real-world problems using physics. I think the main thing that'll keep this from being a widely used product is the initial cost. There's definitely an ROI to look at, because if the tanker you're using can include more methane per load, you'd make your money back. It's just a matter of how much money are you having to make back. What are your thoughts? Put them in the comments below. This technology has several great applications. Safer methane tanks for vehicles, lower energy storage systems, especially for remote power generation. For more science and tech updates, remember to like and subscribe, and remember, keep asking questions. I'll see you on the next video.